So we will next move on to another important property of schedules, which is the recoverability. Now what has been, we have been studying in the serializability, in the conflict serializability and the view serializability, is that whether they are equivalent to each other, assuming that all the transactions in the schedule are correct. That means they, all the operations they are successfully done, processed. Now what happens in most transactions, it may happen that the order, the transaction may abort, etc. So whether the transaction can recover or not, that is the study of recoverability. So essentially in the serializability study, we did not take into account the commits and aborts and their order, more importantly the order of when a transaction commits and when a transaction aborts, etc. That is what we are going to next study. So this is on recoverability of schedules. So recoverability of schedules. Okay, so here the essential idea is that the order of commits and aborts in the transactions are important. Now the first thing is, we will define, which is something called a recoverable schedule. So a schedule is said to be recoverable if certain conditions happen. So recoverable schedule. Essentially the definition is the following. Suppose in the schedule the transaction Ti reads a data item X that has been previously written by some other transaction Tj as part of the same schedule, of course. Now it must happen that if this holds, then if one holds, then the second condition must be holding is that Tj must commit before Ti commits. So if this happens, then the second condition is that Tj commits before Ti commits. Now why is this? Intuitively we can see what is the reason for this is that Ti has read something that has been produced by Tj. Now unless Tj really commits, meaning it vouches that what it has written is correct, Ti, the reading of Ti may not be correct. So in other words, suppose it happens that Tj now aborts. Now Tj aborts, meaning whatever written by Tj needs to be rolled back or needs to be undone, which means that whatever Ti read, which is the value written by Tj, is also incorrect, because it should not have written read this, because that has been unread. So Ti, if it had already committed, then it is in a problem, because now it has committed with a wrong value read. So that is why this is not allowed, and that is why our schedule is called recoverable if Tj commits before Ti commits, if the first condition happens. Now let us directly jump to an example and let us see what we are trying to say. So suppose the schedule is the following, is R1A, then there is a W1A, then there is a R2A. So the transaction 2 then reads, and then suppose transaction 1 reads some other data item. Okay. Now essentially what is happening is that you see that transaction 2 is reading the A which is written by transaction 1. Now in that case the rule says that Tj must commit before Ti commits. Okay. Now suppose what happens is that, let me introduce this thing, is that suppose after this there is a commit by C2 here. Okay. Now the question is whether this schedule is recoverable or not. So this is not recoverable. I am assuming that okay, C2 commits here and then C1 commits here. This is not recoverable because C2 should not be committing before C1 does. The reason is, suppose C1, it is not a commit here but it is an abort by C1. Then what happens is that this value that is produced is wrong. That means this read, that what it has done from W1 is also wrong. However, it has already committed. So by the time the system reaches here and finds that this is abort, this is already committed. Committed meaning, if you remember the property of durability, when a transaction commits, it essentially says that okay, if I am committed, then everything that I am going to do is final and correct. Now but that is a problem. So this is not recoverable. So this schedule is not recoverable. Now to make it recoverable, what should have been done is that if this is the case, if this is the schedule, then R2A, then R1B, etc. What it should be done is that C1, So C1 transaction 1 should first commit and then transaction 2 commit. So this order of commits is very, very important. So that's the reason of recoverability. So that's the reason why we studied recoverability. This order of commits and aborts is what we are very much bothered about, because that is when a schedule may be recoverable or may not be recoverable. So fine. Now the reason this works is that suppose just like the previous case, somehow this commit is not true but this actually aborts. Now if this aborts, that means this value produced is wrong, that means this R2 should also be wrong, which is fine, because then the transaction 2 can then simply abort instead of committing, because it has read a wrong value, it can also just abort. So then there is no problem as far as the recoverability of the schedule is concerned. So that is the recoverable. All that seems to be fine, but then it runs into one problem which is called the problem of cascading rollbacks. By the way, this rollback is essentially what the undoing operation etc. is. So when an abort happens, a transaction essentially rolls back. That means that it undoes all the values and writes the old values of etc. So that's a rollback. Now the problem is, even if a transaction is recoverable, there may be a series of rollbacks. As we saw in the other the previous example, if there is an abort by transaction 1, then this leads to another abort by transaction 2. So in a general sense, this may lead to another abort by transaction 3 and all these things. There may be many rollbacks just because one transaction aborted or one transaction rolled back. So this is a series of cascading rollbacks. So that problem may be there even if a transaction is recoverable. So now just to highlight the point a little bit better and just to give an example, suppose this is the schedule is R1A, then there is a W1A, then there is an R2A, then there is a W2A, then there is an R3A, then there is a W3A, etc. Now as we said that because to make it recoverable, it should happen that R1 should first commit, then R2, then R3, right, that is fine. But suppose R1 somehow decides to abort, there is some problem. Now if since R1 aborts, R2 must also abort, that means this should abort. Now this, because this is aborted, then R3 must also abort, so that's the thing. So that means A1 leads to aborting of A2 and then leads to aborting of A3. So by the way, A1 stands for abortion and C for commit. So commit and abort are C and I. So that's a series of rollbacks. So that is the problem with recoverable schedules, is that even though it is fine in the sense of correctness, but it may lead to a lot of work being undone. So there may be a lot of time to recover because lots of aborts are done and lots of time it takes for the schedule, for the database to recover. So the next concept that comes in this space is the concept of cascadeless schedule. So to avoid this problem of cascading rollbacks, we define what is next called a cascadeless schedule. So essentially cascading rollbacks are eliminated. So there are no cascading rollbacks. If a schedule is cascadeless, that means that there should not be any cascading rollback. Okay, and the more formal definition is the following: is that if transaction Ti reads X which is written previously by transaction Tj, then it must happen that transaction Tj commits before Ti even reads. So note the definition, note the difference of the definition from the recoverable schedule. In the recoverable schedule, the first condition was the same. So if Ti reads something which is written by Tj, Tj must commit before Ti commits. That was in the recoverable schedule. In this new cascadeless schedule, Tj must commit even before Ti has read. Now the intuition should be very clear why this is being made. The intuition is the following: is that if Tj commits before the read is being done, so if Tj is successful, that means the read is correct. There is no problem with the reading. If however the Tj is wrong and it has aborted, it can be argued that the Ti has not wasted any operation, Ti has not even read from Tj, so Ti by itself does not need to abort because it has not even done anything which is dependent on Tj. So that is why it avoids the cascading rollback of Ti if Tj rolls back, and that is the definition of cascadeless schedule. Okay, so here is the example Once more the same example we will follow as we did. So it's R1A, W1A, then there is an R2A and R1B. Now the original problem was if this abort happens, then this commit should also be changed to abort. This is why this was recoverable but not cascadeless. Now to make it cascadeless, what needs to be done is the following: is that R1A, W1A, then it cannot be that R2A does before A1 does. So transaction 1 must commit, but for transaction 1 to commit, it must complete this operation. So R1B, then transaction 1 commits, and then transaction 2 starts doing whatever it wants to do, because this read depends on this, right? So this commit must happen before this read happens. So now you see what is the good thing about this is that even if this aborts, then of course transaction 2 has not done anything at all. So it will just simply not start and it doesn't need to abort. The question of aborting or commit doesn't arise for T2 because it has not started doing anything at all. So this is not the first example, this is not cascadeless but recoverable, but this is cascadeless and recoverable. Okay. So essentially the idea is that no completed transaction needs to roll back, because T2 has not completed, so it doesn't need to roll back. So no completed transaction rolls back. That is the effect of these cascadeless schedules. Okay, fine. So that is the definition and the property of cascadeless schedules. Now one thing is that there is a connection between cascadeless and recoverable, just like view serializability and conflict serializability. There is again a connection between cascadeless and recoverable. As we saw in the example, that the first example was recoverable but not cascadeless, and the second example was cascadeless, and if you had noticed, it is also recoverable. Now this is not an accident, so we can put this down as actually in the following manner: is that every cascadeless schedule is necessarily recoverable, Now this is again, this can be shown in two ways. From the intuition we can see, plus also it can be actually proved quite easily from the definition. Now the definition of cascadeless says is that Ti doesn't read before Tj commits. That means that Ti cannot commit, of course, because Ti is a reading operation. The commit is the last operation of a transaction. So if Ti reads after Tj commits, then it of course means that Ti commits after Tj commits. So that means every cascadeless schedule is necessarily recoverable, but not the other way around. And we saw examples why it is not the other way around. So that is fine up to this cascadeless schedule. Now this all seems to be correct, but there is still a little bit problem that is left even after cascadeless schedule, is that the problem of writes remain. So the problem of writes remain in the sense is that a later transaction, so all the cascadeless schedule etc. says the transaction Ti reads what has been written by Tj. Now which means that nothing is said about the writing of transaction Tj. Suppose the same data item is written by Tj. It doesn't read what Ti writes, but it simply writes the same thing, and then it tries to commit before the commit of Ti happens. Now that is also of course wrong, because it should be writing afterwards, not earlier. So the problem of writes is not handled, not talked about at all by recoverable and cascadeless schedules. So the next definition is that of strict schedules, where it tries to handle this situation with the writes. So let us first look at definition of this. So essentially it's kind of the same thing. If Ti reads or writes, this is the change here, Ti reads or writes X which is previously written by Tj, then it must happen that Tj commits before any of this read or write operation is done. So before Ti reads or writes. So it is not just about read, it is also about write. So it enhances the definition of cascadeless to include the writes. So that is why this is, so it is something more than cascadeless. So it is very strict. Okay. So now let us go to the example. Suppose R1A, then W1A, then there is a W2A, then R1B. Okay. Now essentially what it says is that this is commit by C1 and then commit by C2. Fine. So up to this part is fine. Now this is not strict. This is not strict because this write on the same data item X is happening before C1 commit. So this is not strict. Although this is cascadeless. This is cascadeless, but this is not strict. So this W2 should have happened before C1. Now to make it strict, what the following thing needs to be done. So this R1A, W1A, then of course R1B, then commit, and then this W2A and C2. So this makes it strict. Okay, now the question is the connection between strict and cascadeless. Again, it can be very easily seen that every strict schedule is cascadeless, but of course not vice versa. The reason is, so this is an example to show that this is cascadeless but not strict, but otherwise it can be again very easily understood from the definition. So strict argues when Ti reads or writes from Tj, and it should, the commit must happen before reads or writes. So if you just take reads, of course the reads or writes covers that read. So that means that every strict schedule is of course maintains what the cascadeless schedule tries to say. So it is of course cascadeless, but not the other way around, because this is an example. The first example actually shows that. Now okay, all that seems to be fine, but the question is, why is strict important? I mean, why do we bother about this writing of A? And before what happens, what is the problem with this schedule? I mean, okay, this we are saying that this is not strict, etc., but what is the problem? The problem is the same as the earlier one, is that, okay, so this the problem is the same as what we have been seeing in the view serializability, is that W2A is essentially a blind write. Now which means that W2A may have read some other value, and if transaction 1 by itself aborts, it may not be correct that transaction 2 simply blind writes and then successfully goes through, successfully commits. It should not be happening. So again, it's a completed transaction that is allowed before it depends on some other transaction. So essentially the write after write conflict is not taken care of. To take care of the write after write conflict, it must happen that the next write W2A must wait for the W1A to finish successfully, which means it must wait for transaction 1 to commit. That's the big thing. That's the way. So that is why this is strict. Now just to complete the story. So by the way, just one very interesting thing is to say that every serial schedule. So what is a serial schedule? Just to refresh your memory, it's a one transaction happens, then completely commits, and then the next transaction starts and then completely commits, and then the third transaction starts. So every serial schedule in which this follows is of course strict, right? Because before the transaction 2 does anything, whether it's read writing the same data item, etc., the transaction 1 has committed. So it is of course strict, which means it is also cascadeless and recoverable. Now here is a nice Venn diagram to think about. So there are these serial transactions. This is serial. Now if it is serial, it can be also thought of as, so there are then these things which are strict. So serial transactions are strict, but there are other schedules which are also strict but not serial. Then there are cascadeless schedules, which every strict is of course cascadeless but not the other way around. And then finally there are recoverable schedules. Alright, so that seems to be a nice Venn diagram. Now if we repeat the Venn diagram if we go back to the concept of serializability, and we can produce a similar Venn diagram. So serial, if it is serial, that means that it is also conflict serializable, but of course there are other conflict serializable schedules which are not strict. And every conflict serializable schedule is also view serializable, but not the other way around. So you can again think of some another Venn diagram like this. Now the question is, these are two Venn diagrams, and let me kind of very quickly abbreviate them and write down what I am trying to say. So suppose this the serial schedule is S. Okay. Now that is your this thing. So what is the connection? Essentially what I am trying to say is what is the connection between recoverability and serializability. And here is the Venn diagram that it shows is that suppose, so this is your, let us say, conflict serializable, then let us say this is your view serializable, then there can be schedules which are strict. So this is strict. Okay. So what does it mean? That there are schedules which are strict but neither view serializable nor of course conflict serializable. Then there can be strict schedules which are view serializable but not conflict serializable. Then there are strict schedules that are conflict serializable, and that means of course view serializable but not strict, and so on and so forth. Then strict, and then there can be this cascadeless, and then finally there can be recoverable. So apparently all possible combinations are there, and of course just to complete this, this is the entire space of schedules, and there are some schedules which are not at all view serializable and not recoverable. But the interesting part is here is that the serializability and recoverability apparently can take way in any part. So there can be schedules which, so the recoverability is independent of the serializability. So whether the schedule is recoverable or not says nothing about whether the schedule is serializable or not, and vice versa. So apparently you can find examples for all of them, and that's a nice thought example or whatever. You can do this, that's a nice homework for you to do about, just think about can we get examples of schedules which follow in one of these things and not the other. So all the portions of the Venn diagram, can you get examples of all of that? Alright, so that completes the module on schedules, and we will next start on concurrency control protocols in the next module.